Okay, thank you very much and welcome back. I always find it amazing that in science we deal with very difficult problems. In computer algebra we have very fancy algorithms. People are doing AI and all kind of very sophisticated stuff, but the problem of connecting a laptop to a projector has not yet been solved. So take this as an open problem for the future. Okay, good. So apologies for the delay. Let me just continue where we stopped yesterday. And yesterday I introduced univariate D-finite functions, and it's very analogous if you look at the shift case. So when we talk about sequences, and I just go quickly through this also as a reminder of what I told you yesterday. Everything is very parallel to the D-finite case. So if we have a sequence of numbers or other objects, an that is indexed by the natural numbers, we call this sequence p-recursive if it satisfies a linear recurrence equation with polynomial coefficients. So the shape of such an equation is given here. And again, you can think of polynomials or rational function coefficients. This doesn't really make a difference. Examples, well, again, the constant sequence definitely falls into this class than any polynomial sequences. A prominent example is the Fibonacci sequences, where you have even constant coefficients and you don't need polynomials here. Then things like n factorial, 2n choose n. So the hypergeometric terms that are introduced on Tuesday, they also fall into this class, because if you have that fn plus 1 divided by fn is a rational function, you cross multiply and you get a first order recurrence. So this is just a special case of this. And then things like harmonic numbers and many other things fall into this class. And like for D-finite functions, we have certain features, namely that it is a very rich class and very useful class of sequences. They are also called p-finite or D-finite or also holonomic. So this naming is really just a mess. While D-finite referred to the fact that it's differentiably finite. If you differentiate it, you end up in a finite dimensional vector space. The name p-recursive refers to the polynomial coefficients. So this is not really nice, but this is how it has historically grown. Anyway, I will not insist on this name, and in the future only talk about D-finite and mean everything. Like for D-finite functions, we have many closure properties that I will show in a second. And again, it's a good data structure because we need only finite amount of information to describe an infinite object, an infinite sequence, namely the recurrence and finitely many initial values. And again, everything can be executed algorithmically in the computer. So here is again a list of examples. If you look very carefully and you realize that there's a lot of overlap with the examples for D-finite functions, then this results from the fact that some of those, like we will look at the Legendre polynomials as a prototypical example, they are functions that depend on two parameters, and it's D-finite with respect to the continuous variable, and it's p-recursive with respect to the discrete variable, as we will see. And then, of course, there are all kinds of combinatorial sequences here, Fibonacci, Fibonacci, gamma function, whatever. So yeah, we have seen that the gamma function is not D-finite. It even doesn't satisfy any algebraic differential equation, but its functional equation, since it generalizes the factorial, is a very simple p-recursive recurrence. So it's a p-recursive sequence. Yeah, Motzkin numbers, Luca's numbers, these are things that appear in combinatorics. Okay, about the closure properties, they are more or less the same as for D-finite functions. So this is also a good recap of yesterday. Not yesterday, Tuesday. So if an and bn are two p-recursive sequences, then their sum, respectively difference, is again p-recursive. And the proof, as we have seen, is done by linear algebra. It's very elementary. The product is again p-recursive, and I can say that also here the proof is the very same scheme. You express everything in terms of the basis and then you solve a linear system. So this is simple. Then for D-finite we had that the antiderivative is again D-finite, and here it's the antidifference or indefinite sum, as we have seen in Gosper's algorithm. So any sequence Sn that satisfies that their difference gives An is again p-recursive, and the proof is very simple. In the recurrence you replace every occurrence of An by this forward difference, and then you have a recurrence for this indefinite sum. For D-finite functions we were allowed to do algebraic substitutions. Here we can do integer linear substitutions, so n is replaced by Cn plus d with integers c and d, and then the result will again be p-recursive. Okay, and as for D-finite functions, we introduce operator notation for p-recursive sequences. So I denote by Sn the forward shift operator. So Sn applied to An is An plus 1. And if I do this twice, I get An plus 2. This is very much the same as for the differential operators. Then we denote by Kn, Sn, the ring of operators, of difference operators with rational function coefficients. As in the differential case, this is a non-commutative ring. Here is the commutation rule. If you multiply Sn by n and you switch, then you have to replace the n by n plus 1 because of the action of this shift. Or more generally, if you have a rational function and you want to move the operator behind it, then you replace n by n plus 1 in this rational function. And so here's the example, the Legendre polynomials. In the last lecture we have seen if we differentiate it with respect to x, we get a second order differential equation. Now we take the other variable, the index n, and we look at shifts with respect to n, and then since this is a family of orthogonal polynomials, it's a classical result that it satisfies a three-term recurrence of a certain shape, and here it is. Well, and again, if you write this as operator, it becomes more compact and more convenient to deal with in a computer algebra system. Okay. And again, we can make this connection. So we can say a sequence is p-recursive if there exists an operator in this ring of operators that is not 0 and that kills the sequence. And certain closure properties can again be expressed in terms of operators. So if you have two sequences and they are annihilated by L1, L2, then the anti-difference, as we have seen, is just this. So you have this Sn minus 1. This corresponds to the forward difference, An plus 1 minus An. And then you compose this with the original operator, and then you get an operator that annihilates the indefinite sum. If you want to look at the addition of two sequences, then it's again the LCLM, or as we saw, any multiple would do the job, but the smallest is the LCLM. And again, it is something more general, so this is really very much the same. And if we have an inhomogeneous recurrence, so where on the left-hand side we have a linear polynomial coefficient operator, and on the right-hand side we have something that is again p-recursive, we can homogenize the recurrence and get that this An is also p-recursive. Okay, so just to state this, that there's of course a connection between D-finite and p-recursive. So a sequence An is p-recursive if and only if its generating function, that is this formal sum An times x to the n from 0 to infinity, if this is D-finite in the sense as I introduced on Tuesday. And also today, let's do a quick proof that is just rewriting. So you look at the derivatives of f. So you differentiate this generating function and you get this. if you do this many times, you get something a little bit more complicated. You get here factors that I have written using the Pochhammer notation. Well, and okay, you can shift this, then it becomes a little bit nicer. So now if we assume that f is D-finite, so it means it satisfies an ordinary differential equation, linear of this form. So we have certain powers of x, we have cleared denominators so that we really have polynomial coefficients, and we have the derivatives of f. Then we plug this in. Okay, we get this here. And then we do a little bit of rewriting. Here again shifting this sum so that here everywhere we have x to the n. And then putting things together. And we see this is nothing else but a recurrence equation for the coefficients for the sequence members an. Okay, so this is very classical. I don't want to talk much about the Q case, but I have one slide so that it is at least mentioned. There is, so we have now seen the differential case that was D-finite, the shift case that was p-recursive, and then there's a third thing that is called the Q case, where we consider Q difference equations. So the Q difference operator takes, if it acts on the variable x, it sends x to Q times x. And Q is a symbol that is introduced. Or if sometimes in combinatorics you prefer to write it in terms of powers of Q, and then Q to the n is sent to Q to the n plus 1. So then this x plays the role of Q to the n. Likewise, you can write differentials, like Q differentiation. One way to define it is like this. But you see that it's really the same as the Q shift here, basically. Well, and then there are all kinds of objects that satisfy such equations. For example, there's a generalization of the usual Pochhammer symbol in the Q setting. It's the Q Pochhammer symbol. So it's it's this product. And then using this, you can define Q binomial coefficients that are just generalizations of the usual binomial coefficients. When you send Q to 1, then you get the classical binomial coefficient. Also, the trigonometric functions have Q analogs, and many of the special functions have Q analogs, like Q Gegenbauer polynomials, Q Legendre polynomials, and so on. And there's a whole business about all this Q stuff that I'm not going anymore into detail, but basically everything that I tell you in the differential or shift case has an analog in this Q case. Okay, now so far we have looked at univariate functions and univariate sequences, but the goal is to talk about multivariate D-finite functions. So we want to generalize what we have seen to a multivariate setting. And as I said, from now on, I will not anymore talk about p-recursive versus D-finite. But I call everything D-finite, whether it's in the shift case or in the differential case, or we can be in mixed cases. So D-finite is now the word for everything. Of course, we could either go specialized, that we generalize the differential setting to multivariables. That means we have a function f in several variables x1 to xs. They are all continuous, and we can operate on these variables by differentiation. Well, and then the LODE that we had in the univariate case now turns into a system of partial differential equations. And to be D-finite, we have certain extra conditions on this system that you could formulate as being maximally overdetermined, or I will give a more precise definition in a minute. Well, in the shift case, that means you talk about multivariate sequences, and each of the indices, n1 up to nr, you can shift. So you get multivariate recurrence equations. Of course, we again want to have polynomial coefficients. Well, of course, also the Q case can be generalized to several variables. This is now not so interesting. And then you can mix the thing. You can, we have already seen the example of the Legendre polynomials, but this works in very generality, that you have something that depends on certain discrete variables and on certain continuous variables. So then you have mixed differential difference equations that these functions satisfy. And if certain additional conditions apply that I will show on the next slide, then we talk about, again, about D-finite functions. And so examples are all these special functions that were already alluded to in previous parts of this lecture. Okay, so here's a first attempt at defining this D-finiteness in the multivariate setting. So let f be such a function that depends on several discrete variables n1 to nr and some continuous variables x1 up to xs. And then we say this function f is called D-finite if there is a finite set of basis functions. And so these basis functions, they are just certain shifts and differentiations of the original function. So they are integers j1 to jr. They could be all 0. For example, and here we have I first derivative with respect to x1 and so on. So if there is a finite set of such instances of the function such that any member of this infinite family, when I let the i's and the j's be arbitrary, if any member of this infinite family can be reduced to a linear combination of my basis functions. That is like in the univariate setting, you have this recurrence, and the recurrence allows you to reduce any shift of your function to a finite set of basis functions, like the first r shifts when r is the order of the recurrence. We have seen this in the proof of closure properties for D-finite functions, where also I said if you have any derivative of our function using the differential equation that is satisfied, we can reduce it to a finite set of derivatives that is bounded by the order of the differential equation. And here is the very same thing in the multivariate setting. Okay, and this linear combination should be over the field of rational functions in all these variables. And what we get is that, again, such functions can be represented by a finite amount of data. Namely, we have to store the recurrences and differential equations that this function satisfies, and finitely many initial conditions that correspond to this finite set of basis functions. Well, again, it is more convenient to represent this in the language of operators. So recall that this was the notation for operators. In some places, I will use a generic symbol if I don't want to specify whether it's the differential operator or shift operator. Then I use this partial die. And this is where the name Ore comes from. That in general, we talk about Ore algebras or general Ore operators that have a commutation relation like this. So if we have this operator and we commute it with some element from the rational function field, then it is sigma of A times D plus delta of A, where sigma is an automorphism and delta is a sigma derivation, so that resembles of the Leibniz rule, except that here we have this sigma of A, so it's tweaked a bit. But yes, please.
In the
oh yeah.
In the multivariate case, just as the previous slide, so I'm trying to better appreciate the difference with the differential algebraic equations when you have derivatives. So we have polynomials and derivatives and variables.
Well,
is it a special case?
Well, here everything is still linear. So here I'm only talking
Okay.
about linear equations, not
polynomials.
differential algebraic equations. Yeah, and that makes things much simpler.
Okay. So I can so this is a special case of so
Sure.
LPD, a special case of TAs.
Sure, sure.
Differential
And
algebraic
so the
equations.
nice thing here is that you have a finite basis of solutions, which
Yes.
is not anymore the case if you consider these kind of
In
more
the general
general
case, yeah. Okay.
functions,
Yeah, thanks.
equations. Yeah. Okay. So now using operators, we now can talk about the multivariate operator algebra that, well, is called an Ore algebra. So we have rational functions in many variables, and then we have certain operators that act on them. And they could be differential operators, could be shift operators, could be Q-shift operators, but I will not talk about those. Okay, there's a traditional, more complicated notation for such kind of algebras where you also explicitly give this sigma and delta for each of the operators, but well, with our convention that D is always the differential and S is always the shift operator, we can save this long notation and replace it by this shorter, a bit sloppy notation. So, well, if we again look at the Legendre polynomials, we have two variables, x and n. We can differentiate with respect to x. We can shift with respect to n. So we get this Ore algebra that is suited for representing the relations that are satisfied by the Legendre polynomials. And once we are talking about a function, we can look at the set of all operators that annihilate this function that is called the annihilator. So if we have a function f and we fix an Ore algebra O, then the set of all elements in this operator algebra that send f to 0 is called the annihilator. And the algebraic structure of this annihilator is that it is a left ideal. So if you have some operator that annihilates your function, you can multiply it from left by anything and it will still annihilate your function. And so from now on, when we deal with such kind of multivariate D-finite functions, we will naturally deal with such kind of left ideals with these annihilators. Well, and once we talk about ideals, then of course Gröbner bases are not far away. And they also play a decisive role here. So let's look at an example. We have seen the Legendre polynomial several times, and I told you that they satisfy this second order differential equation, and they satisfy this three-term recurrence. And we also have seen that we can write these two equations in operator notation like this. And so it is true that these two relations generate the annihilator of this function. However, they are not a Gröbner basis. And this is something that is maybe a bit surprising if you are not familiar with this non-commutative setting, because if you think of these two polynomials as commutative polynomials, well, then you have one polynomial whose leading monomial is d square, and here the leading monomial is s square, and then usually the product criterion would tell you that this is already a Gröbner basis. However, in this non-commutative setting, this is not the case. So now let me switch to here, and let's go here. So these are the two equations of the Legendre polynomials. We convert them into operators. This is done with this command to Ore polynomial. And now we can compute the Gröbner basis of these two things. And you see something happens. We don't get the same thing back. So the second operator is the same as this one, but here we get one with lower order. Instead of s square, we have leading monomial s. So, yeah. So this is the result. And So we see that here we have 2 monomials under the staircase. That means this is, we say this is a holonomic function of rank 2.
Can we give a meaning of like I don't a geometric meaning to this first equation we found when computing Grobner basis that's mixing dx and
this
Sn?
one, the mixed equation, I'm not aware of any geometric interpretation. It's a mixed differential relation that you may find somewhere in the literature also, and it follows from the other 2. Okay. So if you write down 2 arbitrary operators like this with random coefficients, then they usually will not be compatible. If you then compute the Grobner basis, you will get 1. So it somehow, it has to do with the compatibility of these 2 equations. Okay, so now let's formulate the D-finiteness in this algebraic setting. We fix an Ore algebra and the function f. And now we can say this function f is D-finite with respect to that given algebra if the set, so this is somehow mimicking the definition that I had on the previous, on the 2 slides before. So if the set of all its shifts and derivatives, so that means if you take any member P of your operator algebra and you apply it to f, well, then you get something where you have differentiated and shifted and so on. And so if all these functions form a finite dimensional vector space. So this is really the same thing as this one, right? That there's a finite basis of functions over the field of rational functions in all these variables. Okay, and well, this is nothing else but saying that if you take the quotient of your ring with the ideal, with the annihilating ideal, and you look at the vector space dimension over the rational function field, then this is a finite dimensional vector space. Or in the language of algebra, we say that this ideal is a 0-dimensional ideal. And of course, I should always say left ideal, but I'm sloppy and sometimes omitting this. So this is the picture that everybody is familiar with. So in 2 dimensions, well, we have a Grobner basis, we have a finite set of monomials under the stairs, and the number of these monomials under the stairs, this is what we call, either some people call it the degree of the ideal, or here we usually call it the holonomic rank of the function. And we have seen for the Legendre polynomials, this rank was just 2. So this is a different picture, not for the Legendre. Okay, and now let me give a small application of how that you see that is useful to compute in these ideals, what we can do with that. So at the very beginning of the first lecture, I showed you some set of motivating examples, and one of these examples was to find special evaluations of hypergeometric functions. And so here I show you how this works. This is a work by somebody called Ebisu, and he came up with a strategy to detect evaluations of 2f1 functions. And he has written a long paper. He found 100 of them, so there's many tables. And here is one example that I show you. And so how does that work? We have seen already that with Zeilberger's algorithm, we can compute recurrences for the 2f1 function. And in particular, if I had shown you that for the, so we have here this ABC that I abbreviate here with alpha, that if we compute the recurrence with respect to A, we get a second order recurrence, and similar for B and C. That at first glance could give you the idea that maybe this has holonomic rank 8 because this multiplies, but in fact something similar that what I show you on the previous slide happens, that actually the rank is much smaller, because when you compute the Grobner basis, then things combine nicely and get smaller. So the holonomic rank is 2, like for the Legendre polynomials. And if the rank is 2, that means whenever you take 3 members, 3 instances of this function, and instances, I mean you can take shifts or derivatives, whatever 3 instances you take, you will find a non-trivial relation, because all these things live in a vector space of dimension 2. So in particular, we can look for a relation of this form. That is, we have the function itself that is here. We have its derivative with respect to z. And then here we take another instance that is a shift. So beta is a concrete shift vector. For example, 2, 2, 1. But you can take any numbers. And for any numbers you take, you will find such a relation. And so you divide by this coefficient, and then you get here 2 rational functions that characterize this equation. Okay, so these are rational functions in all these 4 variables. Now, what you do, you look at this rational function q, you look at its numerator, and you try to find values for all these variables, a, b, c, and z, so that this function vanishes. Well, and then if you look, then in this equation, this term goes away, and what you find is a nice relation between 2f1 and its shifted version that, if you unroll it, is like more or less like a hypergeometric recurrence. You get a closed form. Yes, this is what I just said. And then, so let me show you how this works. So instead of taking the recurrences that we already derived, I compute the annihilator from scratch. And so here you see we get the 2nd order differential equation, and then all the other members have leading monomial of degree 1. So that shows that really it's holonomic rank 2. Well, okay, so I wanted to demonstrate something else. If somebody gives you this identity and asks you to prove it, well, then you can do it. And this is what I wanted to show first. So what we have done, that means we compute a recurrence for both sides of this identity. So for the right-hand side, this is very simple. So we define here the right-hand side. No, I did it differently. Okay, so I take the generic annihilator for hypergeometric a, b, c, z. I do the substitution. A goes to 2t, b goes to whatever we have here, this substitution. And we get that, well, this satisfies this equation. Or alternatively, you can just plug this expression into the command and you get the same result. And now you apply this operator to the given right-hand side, and you find that it is 0, so it satisfies this recurrence. Then you have to compare one initial value, and you're done. Proof. But so what Ebiso is doing is really finding these identities from scratch. So let's assume we don't know that such identity exists. Then we would take the annihilator of 2f1, and we try to find a relation of this form. So yeah, we can use this command, find relation, and we give the support. And so here I choose the shift vector 2, 2, 1. So we have this operator corresponds to this part. Then we have the derivative, and we have 1 that is just the function itself. And so if we run this command, we find such a relation that is guaranteed by theory. So now we extract this coefficient that should be 0. We do this substitution, and we solve for any t. And you see we get a bunch of solutions. And then it's convenient to choose a. Here we have some freedom. It's convenient to choose a equals 0, because then we get a terminating series. And you see that here we get exactly the parameters that that are on the slides. And if you plug it in, then basically here you get this first order recurrence for the 2f1 that has here these nice coefficients. And solving this recurrence, here we have this factor, 2 plus 3t, 5 plus 6t. You get exactly these gammas. They directly arise from these factors. Okay, so you can even discover such evaluations more or less automatically. And this is what this guy did, and he compiled hundreds of entries of similar evaluations. Yes?
So how did you decide what substitution to make when you introduced t?
It's the shift vector. You take this beta. So the beta you fix from the very beginning. And so this is now one instance, and once this is done, you try 2, 2, 3, whatever. Yeah? And then, because you want to go in steps like this, you replace alpha by beta times t.
Okay.
Yes.
Thanks.
Yeah. Okay, very quick about closure properties. This is, there's another question.
So here we fixed 2 to 1 and we found something in gamma. So I guess if I fix, I don't know, 1 to 3, I'm going to find probably something else, etc., right?
Sure. And for some of the shifts you find something, for others you maybe don't find anything, because then the function becomes too complicated and you don't find nice zeros. But yeah, in principle you can play forever with this.
Okay, so I mean, do we learn something about 2 to f1, for instance, after all of those manipulations and equalities with the gamma function?
Yeah, you get a lot of special evaluations, and some people are very much interested in these kind of special values of 2f1 functions.
Okay.
There is another question.
And prolonging the question, so if you fix several betas and try to recombine the q betas linearly by linear combination, do you find relations between those relations?
The q betas for several different betas. So that means you want to find a relation between more than 3 instances of the 2f1.
Yes.
Well,
between several of those that you for which you have those closed form evaluations.
Yeah, but then you get much more freedom, right? Like here, if you fix 3 instances of your function, you get a more or less unique relation. If you do what you propose, you have a lot of freedom of what you can do. Maybe it works. I don't know. But then, you have to make sure that several of these things disappear. So in the end, you want to have 2 things left. You want to have a generalized hypergeometric sequence. Okay, yeah. Okay, closure properties, again, addition. So here I put some examples. Multiplication, we have substitutions, and now it depends. So again, for the continuous variables, you can substitute algebraic functions. For the discrete variables, you can do this integer linear substitution. Operator application, so we have seen in the D-finite case, we can take the derivative or even the second derivative. And more generally, we can define a new function that arises as operator applied to your original function. Like here, the operator would be d times s squared. So we differentiate and we shift by 2. And you can have more complicated operators. And anything you get by this, because it lives in the same vector space, it is, again, D-finite. And later I will show you that we can also do summation and integration, definite, like with Zeilberger's algorithm. Quick remark about the holonomic rank. Also, this is the straightforward generalization of what we have seen in the univariate case. So if we take the sum of 2 functions, then the holonomic rank of the output is at most the sum of the 2 ranks of the input functions. It's at most the product when we take the product of 2 functions. when we do an algebraic substitution, it's at most the original rank times the degree of the algebraic function. And if we do this number 4, this operator application, the rank doesn't change. This is a nice thing. The rank stays the same, or it could even drop, but it doesn't grow. And so here I put this complicated looking example to make a little demo of this. So this is arose in a paper with Peter Paule and Sergei Suslov, and the latter is a physicist, and he came with these kind of Coulomb integrals. Actually, here are the integrals. So we have two functions, f and g, that are defined in this complicated way, but actually it's not so complicated. It's just because there are so many parameters floating around. But basically f and g are two linear combinations of Laguerre polynomials. And so these alphas, they also hide certain expressions with these parameters behind them. But important to know is just that they are linear combinations of Laguerre and its shifted version. And then, for example, we want to compute the integral of f squared plus g squared. So I don't compute yet the integral, but I prepare the computation of the integral, because first what we have to do is we have to transform this explicit representation of the function into an implicit one, namely we have to compute an annihilating ideal for this function. And so how does this work? Well, if you compute this thing, then I leave away all these parameters. I just set them to 1. So that means we want to find an annihilator for this expression, Laguerre squared, so Laguerre of n minus 1 squared plus Laguerre of n squared, and the mixed term, n times n minus 1. Okay, so we can use the annihilator command and just run this. We take this expression, we use these. Oh, okay, I could have omitted the SP, that is not relevant here, but anyway, so it takes a few seconds. We get something that seems to be quite big. It has 2 megabytes of size, and we can make a little estimate. What holonomic rank would we expect? So Laguerre polynomials is very similar to Legendre polynomials. They have rank 2. So if you remember what I showed you on this slide, well, if we multiply two things, the ranks multiply. If we add two things, the ranks add. So that would mean here we multiply two things of rank 2, that would give rank 4. And this happens 3 times, so very naively you expect rank 12. A bit less naively, you recognize if you take the square of a function, then it's a bit better than taking the product of 2 arbitrary functions. So for those we get rank 3. But that's it. So we have 3 plus 4 plus 3. And as you see, indeed, we get something that has rank 10. So here I compute the monomials under the stairs, and there are 10 of them. And so I use this example to show you that you can use this third closure property, this operator application, to your benefit by realizing that this expression can be expressed as an operator applied to something. And it's a bit tricky here because we have this n that is sometimes shifted and sometimes not. So to deal with that, we first introduce a dummy variable. So I make a bivariate expression where I have in one instance I have m minus 1 and I have n minus 1. Then I apply this operator, 1 plus sn plus sm times sn. And after that I replace m by n. And as you see, you get exactly the same as above. And so now if you use this idea for the closure properties, that means you start with this function in m and n. Okay, you get some annihilator. This has now rank 4. Next, you apply the operator, and there's a dedicated command for this. So again, things get big, but not as big as before. And finally, also the substitution can be done algorithmically, and it doesn't increase the rank. Okay, we get this. And now if we look at the support, well, we see that the Gröbner basis consists of 3 operators with this support, or alternatively, if you look at the monomials under the stairs, we indeed get 4, and the whole thing is much simpler. And this is crucial if you want to compute the integrals. You want to have the input as small as possible, of course. Okay, this was just to demonstrate this thing, that sometimes it pays off to deal cleverly with these different closure properties and not do it blindly and naive. Yeah, I think I skipped this example. I have shown this in Paris already in November for those who were there. Now I really want to approach the summation and integration of D-finite functions, and there is a little technical detail that I want to address quickly. So I have already mentioned this name of holonomic functions, and in the case of univariate D-finite functions, I just said, well, this is the same. We can call it either way, and it doesn't matter. In the multivariate case, there's a little subtlety, namely that D-finite and holonomic is not always exactly the same. Well, here's the definition of what we understand by a holonomic function that is slightly different than the D-finite definition. So let's first look at the differential case. So we have a function f in several continuous variables. And now we define the so-called while algebra that is very similar to the oral algebras that we have seen, with the only difference that now we do not look at rational function coefficients, but only polynomial coefficients. So instead of rational functions in the x, we have now polynomials. So in principle, you can see this as a polynomial ring in 2 times s variables. And again, there's, of course, non-commutative multiplication. And you can ask which operators in this while algebra annihilate my function. You get an annihilator with respect to this while algebra. And then, well, the algebraic structure here is different. You cannot get a 0-dimensional ideal. Actually, one can show that there do not exist any non-trivial 0-dimensional ideals in this algebra. But the corresponding thing is that you have an ideal of dimension S. And there is some theory that tells you that this is the smallest possible. So we have 2 times S variable, and S is the smallest dimension that we can get. And if we reach this dimension, then we call the function f holonomic. And the consequence of this is, well, if you have an ideal of dimension S, that means if you fix any subset of S minus 1 of your ring variables, you can find a non-trivial elimination ideal. So you can eliminate these S minus 1 variables, and you will get something non-trivial in your ring that has not these S minus 1 variables. Well, and this is the property that guarantees the existence of integrals, because if you want to integrate with respect to S minus 1 of these variables, with only one variable surviving, then you could do it by eliminating all the other variables and then turning the operator that you get into a relation for the integral. So this is the differential case. The sequences case is done via the generating function. So if you want to know whether a sequence is holonomic, well, you take the multivariate generating function and then you try to fit it into this definition. Okay, I mean, so it looks kind of similar. Now, what is the relationship between D-finite and holonomic? Well, one good news is that as long as you stay in the differential case, there's really no difference. Whether you are univariate or multivariate, D-finite and holonomic is really the same. But in the shift case, this is unfortunately not the case. And here's the famous example. If you take this simple rational function, Well, then because it's a rational function, of course, you can write down recurrence, a recurrence in n and a recurrence in k, and so it is clearly D-finite according to our definition. But, well, if you do a little calculation, it's not so difficult to see that it will not fit into this holonomic definition. So one has to be a little bit careful. And what we do in practice is that, for the calculations, we prefer to calculate over the ring of operators with rational function coefficients. So we are in the D-finite settings, in the D-finite setting, and this usually works much faster than if you compute in this while algebra. So for the computations, we use the fact that the functions are D-finite. However, if we want to do an integral or a sum, and we want to argue that the algorithm terminates and that we will find something, then we have to rely on this concept of holonomy. But so for practical purposes, you could say I ignore this and I just run my command, and well, okay, in the worst case it runs forever, which anyway, even if there's a theory that predicts that your algorithm will terminate, it can still run forever. I mean, forever in practice, you know. So it doesn't really make a very big difference. Okay, close parentheses. Here are some holonomic principles, but more or less they have been stated before. But let me emphasize them again. So whenever we talk about a function or a sequence, we are usually not thinking of an explicit expression. And of course, often they are given as such, but for the computations, we only think about their relations that these functions satisfy. So any function or sequence is represented by an ideal of operators, an annihilating ideal, and of course initial values. Whenever we have an ideal, well, we automatically write it in a canonical way, namely by its reduced Gröbner basis, and then this makes many of our tasks much easier because, as you know, we can decide ideal membership, we can decide whether two ideals are the same, we can decide whether one ideal is contained in the other, and so on. Well, and whenever we want to integrate a D-finite function, or we want to take a sum over a D-finite function, then this is done by creative telescoping, which so far we have only seen for hypergeometric terms with Zeilberger's algorithm, but in the rest of this lecture I will show you how this is done for general D-finite functions, so that the title of my lecture is somehow fulfilled. Yeah, and also for the output, usually you don't get a closed form, but you get some implicit description of your object, which for many practical applications is good enough to extract relevant information. Okay, so also the multivariate thing was initiated by Zeilberger. And actually, this was the seminal paper that started all this business, and then the algorithm that I showed you on Tuesday came a bit later. So this is the starting point, basically, of all this theory. And the algorithm that is given in that paper is based on elimination. So 2 slides before, on holonomic functions, I talked about elimination. And this is what was used in this paper. And well, as you know, elimination can be very costly. So that's why this algorithm was later called the slow algorithm, in contrast to the fast algorithm that we have seen on Tuesday. Okay, so now let's also at the same time do a recap of creative telescoping that we have seen 2 days ago. But now let's assume that f is an arbitrary D-finite function. Well, here I focus on the shift case, so n and k are 2 shift variables. But so last time we assumed it's a bivariate hypergeometric term. Now it can be D-finite of any rank. And so, of course, we have given f by its annihilator, not in a closed form. And to solve, to say something about the sum of f with respect to k, we want to sum f, k from, let's say, 0 to n or whatever. We want to find a telescopic relation of this form, where you see on the left-hand side we have a recurrence equation with coefficients that do not depend on the summation variable. They are free of k, they depend only on n, and they are polynomials or rational functions. And we have the shifts of f, but only with respect to n. And so this left-hand side is called the telescoper, and this will eventually turn into a recurrence for the sum. Well, if on the right-hand side we have something that is of this form, g of k plus 1 minus g of k, which using our operator notation can be written like this. And when we sum over this equation, then this part will go away. And now, as similar to what I said about hypergeometric summation, you may ask, okay, so this g, where should we search for it? And I remind you that, well, you can just write down trivial solutions that are definitely true, but are completely useless because they don't give you any new information, so you want to exclude this. And in the hypergeometric case, we said we look again for hypergeometric terms, and as a bonus, we got that this hypergeometric term, if it exists, it must be a rational function multiple of the original f. And the generalization of this is that for G, we look in this finite dimensional vector space that is spanned by F and all its shifts. That we could write as O, this algebra times F. This is a finite dimensional vector space, and in this vector space we look for this certificate function G. So in algebraic terms, the task is we want to find an operator P that corresponds to this left-hand side and an operator Q that will generate us this G. So G will be Q times F. And then this relation translates into this operator. So this operator should annihilate F, and this is nothing else but claiming that this operator is an element in the annihilator. And now here you see why it is useful to employ Gröbner basis, because such questions we can decide by using the theory of Gröbner basis. So this is nothing else but an ideal membership problem with the twist that here, well, this object we don't know in advance, but we make an ansatz with undetermined coefficients and we force it to be a member of the ideal, which will give us a system of equations for these unknowns. Okay, the same thing for the differential case. It's really analogous. So if we have f of x, y, and we assume that these are the two continuous variables, then the creative telescoping relation looks like this. We have derivatives with respect to x on the left-hand side and a g such that its derivative is giving the right-hand side. And again, g is looked for in the finite dimensional vector space that is generated by the derivatives, by the partial derivatives of f. So we want to find an operator of this form, p for the telescoper, q giving us the certificate, and so that it's an antiderivative of the left-hand side. Okay, so here's a concrete example. Let's assume we want to compute this integral where j is the Bessel function. So this thing here is what I had called lowercase f of x and y. Also the Bessel function has rank 2, and as a basis I choose f and its x derivative. Here is the annihilator for this function, little f. So we see here a second order differential equation, and here a mixed partial differential equation of order 1. And so if we make this ansatz and we do some calculation, we find that this operator p and this operator q, they satisfy this relation that was on the previous slide. So we can find our G, that is nothing else than Q applied to F, and doing the corresponding simplification, we can write it like this. So you see, it's a linear combination of the input function and its derivative, just slightly simplified. Well, and then you integrate over this equation. On the left-hand side, you get a differential equation for the integral, capital F of x. And on the right-hand side, you have to evaluate this g at the integration bounds. And here it turns out that this is 0, so we have natural boundaries. And we find that this integral satisfies this nice second-order differential equation. And then the only thing is, that is now not shown explicitly, you would have to look at some initial conditions and to conclude that this integral evaluates to another Bessel function k of x. Okay, so now a bit more concretely, how do we compute this p and the q? Well, I said make an ansatz, but so how should this ansatz look like? So for the telescoper, the nice thing is that the coefficients are only allowed to depend on x, not on y. So we write it as it is. And we don't know the order in advance. This is the same problem as with Zeilberger's algorithm. So we start from r equals 0, and if we don't find anything, we increase and we continue. And then by general holonomic theory, it's guaranteed that at some point it will finish. The more delicate case is the certificate. And here we take advantage of the fact that everything here lives in a finite dimensional vector space. So we write the operator Q as a linear combination of these basis functions. So if U denotes the set of monomials under the stairs of our Gröbner basis, so you have this picture in mind, so for example 5, and then we know that definitely this operator Q can be written as a linear combination of these monomials. So we can make an ansatz. Q is the sum over all monomials in U with, now we have here unknown coefficients that are bivariate rational functions. So remember, only the telescoper is forced to be free of y. The other part can contain x and y, both. So we have to put x and y here, which is a bit unfortunate, as we will, and this will make our life difficult, as we will see here. So this idea was designed by Frédéric Gissac. So that's why we call it now Gissac's algorithm. Well, I don't have a picture here. You just have to look here. Okay, so the idea of Gissac's algorithm is to make this kind of ansatz. So we want to find P and Q such that this combination P minus dy times Q is a member of the ideal and of the annihilator of the given F. So we make the ansatz for the P. This is the ansatz for the Q with these bivariate rational functions and the monomials under the staircase. Well, now we want to force this operator to be a member of the ideal. So by general Gröbner basis theory, we should reduce it with modulo the Gröbner basis. And then, well, it's a member of the Gröbner basis if and only if the remainder of this reduction is 0. So as long as we do this with undetermined coefficients, of course the remainder will not be 0, but it will be something that depends on these coefficients. And so this forcing the remainder to be 0 gives us a system of equations for our unknowns. However, the problem is, before we do this reduction, we should write this operator in a normal form. And well, we decide that the normal form means that the coefficient is always on the left and the monomials are always written to the right, which we have to make this choice because of this non-commutativity. Well, and then you see here, this dy on the left doesn't make us happy. We need to have it on the right. But if we want to move this to the other side, well, we have to respect the non-commutativity. And so we get here the q, but for reason of this non-commutative calculation, here we get the derivative with respect to y. And so you see that in the end, the system that we get is not just a simple linear system, but it is a system where some of the unknowns appear together with their derivative. So the good thing is that we have to do this multiplication only once, so we don't introduce any higher derivatives, we only get the first derivatives, but it will be a first order system of linear differential equations in these unknowns q, u. Yeah, well, this is basically what I have said. Okay, and then, but okay, fair enough. There are algorithms to solve such systems. There are different strategies. So, well, we have several of these u's, and they will appear mixed in several equations. So it's a coupled equation. That means one strategy is that you first uncouple this system of equations to get a scalar equation in one of these unknowns, and then there's Abramov's algorithm and others that allow you to find rational solutions of this equation, and then you continue and solve for the others. Or alternatively, there are methods that directly take such a system of equations, and I can name Moulet, Baccatou, who has done a lot of work in this direction to find the rational solutions of such a system. Okay, so without going into detail, just to know that this is possible. It's not that easy, but it's possible. So this is about the q's, and at the same time we have to find these unknown coefficients pi. But so somehow when we solve this coupled system, our main variable is y, and all the calculations we do is over the field k of x, over the field of rational functions in x. So this is just a parametrized version of this system, and in the end you can solve for all your unknowns simultaneously. Yes, and as I said, we don't know the r, but we loop over the r and until we find something. So this is somehow the most basic version if we are really in two variables, but of course it gets a bit more complicated when you have really multivariate functions with more than two variables. Then it's not that you want to have a single differential equation for the object, because let's say if we have 10 variables and we do one integration, then the integral depends still on 9 variables, so we need more than just one differential equation to describe it, but we need partial differential equations again, and so we have to do this several times. And the strategy that we use is very similar to the FGLM algorithm, so that it guarantees us that the members that we find will automatically be a Gröbner basis for the annihilating ideal of the integral. Okay. Well, let me not, this is technical. Well, yeah, let me quickly mention this. So I found it annoying that often solving this coupled system of equations is very expensive, and so I designed an algorithm that is reminiscent of the Apagodo-Zeilberger algorithm that I showed you on Tuesday, where we make an ansatz. Well, so this part is the telescoper. This is the same as in Schissach's algorithm, but here the ansatz is a bit more refined. Instead of saying, well, I have an unknown rational function in two variables, and I put it there, and then I do my calculation. Here we try to guess the denominator of these rational functions, and this can be done by studying the leading coefficients of the annihilator. and we have to set a degree bound with respect to y for the numerator. And the point is that now we can so everything that is here in this fraction, that was called q sub u before. This is a single rational function in x and y. And now we write it as with an explicit denominator and with explicit polynomial in y in the numerator, and now the unknowns only depend on x. And so the advantage is, if now you do with this ansatz, if you do all this calculation of bringing the dy to the right and reducing it with the Gröbner basis, you don't get any instances of unknowns that appear differentiated. Everything just appears linearly. So the advantage here is that in the end you only have to solve a linear system for, of course, a potentially higher number of variables, but just linear system over kx. And okay, in many examples this works reasonably well. Well, yeah, I don't think that I have to. Yeah, this is basically what I explained. So let's not go into details. Let me, in the end, just mention a few applications before I come to the outlook. So as the title of this seminal paper says, the main or primary application of this whole theory is to prove special functions identities. And so there are many old books about this that contain long tables of identities, of evaluations, of integrals, of series, sums, whatever. And many of these things can now be done automatically. So let's open one of these books. So this is the Gradstein and Rischig book. It has about 1,000 pages, and you see them here. Of course, you don't see much, so let's zoom a bit. And you see, it's just from the first to the last page, it's just formulas. Thousands of formulas. And so if we zoom in, one of these pages looks like this. Okay, so pick your favorite integral here. Yes, let's pick this one. And yeah, okay, first we have to understand what this is. So this C we have not seen yet. These are the so-called Gegenbauer polynomials. They are D-finite of rank 2. Okay, you can plot them, and it's just a family of orthogonal polynomials. We have already seen the gamma function, and we have seen the Bessel function. Well, and then we can try to prove this identity using creative telescoping. So if we look, let's start with the right-hand side. Or no, what is? Yes, the right-hand side, it doesn't have an integral, so here we just have to apply closure properties. That means we put the expression here and we say annihilator. Okay, we get something not so difficult. Differential equation in A, mixed differential equation in A and in N. Fair enough. And then for the left-hand side, here we have an integral, so we should apply this creative telescoping algorithm. So we give the expression here. In the background, it will be converted into an annihilator. Then Schizak's algorithm is run. And after less than a second, we get an answer. And if we look carefully, so creative telescoping computes us the telescoper P. And because here we are multivariate, we get actually two telescopers. This is the first telescoper, and if you compare, it's really the very same operator than here. This is the second telescoper, and it's not a coincidence that it agrees with the second operator here. And then in the second line, what we see here is the corresponding certificates Q. Well, we have two telescopers, so for each telescoper we get one certificate. And okay, then you should also compare initial values that I don't do here because this is not automated. You have to do it by hand. So this is not really part of this algorithm. This is the part where you have to do a little bit work by hand. Okay. And then, yes, let me conclude with this example. I had to bring this because it fitted so nicely. Yesterday in the afternoon, I get this email from Doron Zeilberger. So yesterday somebody asked me, do you work with Doron at the moment? I said, no, not at the moment. And then I get this email. So he published this paper on the archive, and he made a bold claim that, well, with my package one could prove it, and he's just too lazy to do it, and he doesn't care about the rigorous proof. But okay, now since Mark von Heus found a closed form of a certain recurrence, he says he wants to appease to the god of rigorous mathematics, and so he now asks me, can you do it? And okay, so what is this about? Yeah, actually now I don't have because I had to restart my computer, I don't have the website open anymore. So let me show you here. Let me show what is the problem. And okay, I don't talk about where it comes from. So the problem is we have a sequence dp. P is a discrete variable. This is an initial value. So it's, you see, it's a rational function x. And then it's defined by this relation. So the P's member of this sequence is given by a certain rational function R1 that looks like this. Then another part that is a sum over another rational function R2. R2 looks like this. And okay, it doesn't really matter how it looks like. So it's a rational function. These two things are not problematic. But the third sum says we should take the sum over all the previous values of the sequence and again multiplied by a certain rational function that is given here. Okay, so we studied this sequence, and Doron has guessed a nicer recurrence. So, I mean, you could say this is a recurrence, but this is not a recurrence of the form that we like. It's not D-finite because here it doesn't have finite order. Right? We need to take all the values up to down to p equal 1. So he found a second order recurrence, a p recursive recurrence that looks like this. And he wants to prove that the sequence that is defined by this recursive formula is the same as the sequence that you get as a solution of this second order recurrence, of course, if you choose appropriate initial values. Okay, and my first reaction was that, well, Doron, I mean, how should I do this? It doesn't really work, right? I cannot deal with such sums. But then we realized that actually, so you should not think of taking this definition and derive the recurrence, but instead say, well, let's take this function that is a solution of this recurrence, and let's prove that this function satisfies this relation. And this we can do, because everything that is in this recursive description is just things that we know how to do. So, well, this is the relation we want to prove. Here, this is the recursive description with these rational functions, R1, R2, R3. So if you compute the first few values, okay, you see it's getting more complicated, but it's just rational functions in x. This is the second order recurrence. So we define another function using the recurrence, and we compare that, yes, indeed, they give the same values, at least for the first 6 members. And now, well, we have to deal with each of these things individually. So we want to compute an annihilator for the right-hand side here, or we can say we put everything on one side and compute an annihilator and show that this gives 0. Okay, so for the rational function, that's easy. We don't have to do much. You even can write it down by hand. The second thing is the sum over R2, and so here, if the sum is simple enough, you can really just plug the sum into the annihilator command. It will do the creative telescoping, and we get a first order recurrence. Here we have SP and something. Now the most difficult thing is maybe the third sum, where we have the D sequence in the summand. So what we do, we take the recurrence I extract it from the definition. So here as an operator, we see it's a second order recurrence. Now for this summand, this is now bivariate in I and P, so we have to do a little bit of modification because we have to convert this univariate recurrence, the univariate sequence into a bivariate sequence that is constant with respect to the other variable. So we replace P by I, and we add the relation SP minus 1 that says that now, since we look at DI, this is constant with respect to P, we convert it to a bivariate Ore algebra, and we multiply it with the annihilator of R3. So with the D-finite closure property command. Okay, then we get something. We see things grow. And now we can compute, we can run the creative telescoping. We run Shishak's algorithm. It takes a few seconds. And we get something. And you see, we get a telescoper that is just 1. So that tells us that actually this function is indefinitely summable. Like in the hypergeometric setting, we would say Gosper summable. So what this tells us is that if we take all the rest on this page is the corresponding Q. That is the operator that when we apply it to the summand, we get our certificate G. So this tells us that the summand is really the anti-difference of the function that is given by this operator. That means to compute the sum, we just have to evaluate it at the boundaries, which here is a bit tricky because the summand is not given as an explicit expression that we can just evaluate, but we have to use the D-finite description, the recurrences. So let's compute the certificate. This is this operator applied to the summand, and we don't apply it to the summand, but to the annihilator of the summand. Okay, then we get this. Okay, this is just a sanity check that we don't have to do now. And now we have to evaluate this at the summation boundaries. And again, we can do this with closure properties. So here I replace I by P. And instead of a closed form expression, we get a recurrence, in this case of order 2. And we do the same for the lower bound. That means we have to replace I by 1. And to get now a annihilator for the sum, we have to add these two recurrences, computing the LCLM, and we get a recurrence of order 4. And okay, if you don't believe, you can check. You apply this recurrence to f, you replace f by the sum. For the first few values, you get indeed 0. So we have computed, now we have in this relation, for each part, we have an annihilator. We just have to put them together with the plus closure property, and we get something of order 6. Which means, so we have now that this whole expression satisfies a recurrence of order 6. So if we show that the first 6 values of this sequence are 0, which by the way we did already here, yes, it follows that this sequence is everywhere 0, provided that the recurrence doesn't have any ugly integer roots where it would break down, but as you see, there are no positive integer roots. So this really proves that this identity holds. So this to show you that really everything can be done with these implicit descriptions. Okay, and well, I want to conclude with a little outlook that everything I showed up to now is basically classical, and current developments in this field is so-called reduction-based algorithms that are reminiscent of Hermite reduction for rational functions. Okay, I mean, we can go quickly over this. So we have a rational function, and Hermite reduction writes it in the form G prime plus something, where this remainder has a square-free denominator and is a proper rational function. And maybe I don't have to explain you how this Hermite reduction works. This is really classical. But let me tell you how you can use such a reduction to compute telescopers. And this whole approach is motivated by the fact that in many cases, and we have seen in the example, this certificate part, Q, is much, much bigger than the telescoper. Like in the Zeilberger problem, the telescoper was 1 and Q was a whole page of thing. In the Zeilberger example, we needed the Q, but in many examples, you don't need it. And then it's a waste of time to compute it if you anyway don't need it. So there was the wish of designing a procedure that can compute the telescoper without computing this costly certificate. Let me explain the idea at the example of the differential case. So what you need is some kind of reduction procedure, let me call it rho. That is, you can think of this Hermite reduction. So you give a function from whatever function space you work in, and that reduces it with the following property. So if you give a function f, then there is a function g in the same function space, so that the difference of f minus its reduction is g prime. So this is very much the same. So here we have f. This will be the rho of f, and the difference is g prime. And ideally, you want to have the property that this reduction gives 0 if and only if the function f is integrable. So if really you can write f as g prime, then this thing is 0. And if and only if. So whenever f is integrable, you are guaranteed that the reduction gives 0. And then what you do, you take f and you compute the reduction. So you decompose it as g0 prime plus rho of f. So we get some derivative of something plus a remainder. You do the same thing with the first derivative of f, you get this, and so on. And you continue. And if you can guarantee, and then this is what is the case for these kind of algorithms, you can guarantee that these remainders live in a finite dimensional vector space. So recall, for the Hermite reduction, we have that the remainder is always of the form that the denominator is the square-free part of the original denominator. Well, and if we take the derivative, we don't introduce any new poles. So the square-free part is always the same, and the degree of the numerator is bounded by the degree of this denominator. So this is clearly a finite dimensional vector space. And also in more general contexts, one can show this property. And then this guarantees us that after a finite number of steps, we will find a non-trivial linear combination, which then is really just the telescoper that we look for. Okay, and well, you could make a whole lecture about this business because there was so much development in the past years, starting from 2010 when Bostan, Chen, Shisak, Lee talked about the integration of rational functions. Then this was done for so this is bivariate rational functions. Then the summation case, multivariate rational functions by Bostan, Leray, Salvi. Then the next step was to extend these to hyperexponential and hypergeometric functions. And then there's a paper by Bostan, Dumont, Salvi about the mixed case. And then people went on to higher things like algebraic functions, Fuchsian D-finite functions, whatever this is. And then a few years ago, there was the first solutions, actually 2 solutions by these 2 group of people, one singleton group, Joris van der Hoven, and the group of Bostan, Shisak, Leray, Salvi, who designed a general reduction procedure for D-finite functions to do integration. And there are also work for the shift case based on integral bases. And there's a typo, sorry. And another approach by Brochet, Salvi. And I saw in the program today, Brochet will talk about something related to this for multiple integrals. So this is still ongoing. And with this, I would like to end and thank you for your attention.
Questions? Or you had all your questions during the talk? Yes.
Hi, Christoph, I have a question about when you compute like the monomials under staircase, you never specify the order, the like monomial ordering. Is it fixed or there is like the best one, or why is that?
Yeah, of course, any order works. It doesn't matter, and it depends on the example. Sometimes you can get a nicer thing by switching the order. But I mean, in my package, I have a degree order as a default, and if you wish, you can use a default.
So in principle, it may be beneficial to play with the order.
Yeah,
it's just for simplicity. Okay.
Sure, sure. There are examples. Sometimes it already suffices to use the same monomial order, but switch the order of the variables. This can make a big difference.
Okay. Yeah. Thank you.
Other questions? No. Okay, so then let's thank Christoph again for the beautiful talk.